And take it away.
All right, thanks. Great, yeah, so today I'll be talking about data access on the planetary computer with STAC. So speaking of the Pangeo showcases, this will be somewhat similar to the one that I did last week for the Pangeo showcase, but we'll be going into a bit more detail since we have a bit more time. Yeah, so and the other thing, another follow-up thing is, so Matt Hansen gave a talk to this cluster last month, covering some similar things. So you can kind of view this as a part 2 to that talk. So he showed an example of using STAC for remote sensing data on the planetary computer. So we'll be covering that, and then also how we're using STAC for all the different types of data that we are offering on the planetary computer. But first, I want to kind of go over like why Microsoft is involved at all, and like some context about the team I'm on. So I'm on the Sustainability Solutions team inside Microsoft's Environmental Sustainability Program, which was formed kind of recognizing that there's a lot of risk related to climate change, changing environments for both us, for Microsoft, and for our customers. And so that's why last year, 2 years ago, Microsoft set out a few goals that are generally related to climate. So first being carbon negative by 2030, and then by 2050, removing all of the carbon Microsoft has emitted over its entire history. Water positive by 2030, zero waste again by 2030, and then setting aside various goals around protecting ecosystems, one of which is setting aside more land to protection than we use. And then the second part of that is where my team comes in, the team that I'm on, which is the planetary computer. Which basically is a recognition that many environmental sustainability problems look a lot like geospatial data analysis problems. So in order to be able to monitor, model, and manage the natural world, we actually need to have some tools to help us do that are very much in the big data and big geospatial data regime. So that's where the planetary computer comes in. It's a nice umbrella term for a few different things. So this group's probably pretty familiar with the benefits of data in cloud optimized formats available through scalable APIs like Azure Blob Storage. So that's kind of the heart of the planetary computer is a whole bunch of data in blob storage. And like that's really nice to have. It's a lot of work to get there, but we also think that it's important to have various APIs available to users to make that data easier to use. And so we'll see examples of that, but the primary one we'll be focusing on is our STAC catalog and STAC API. And then users, it's helpful to have a place to do your analysis from, especially in a way that's kind of cloud native. So that's why we have this Jupyter Hub available for our users. You log in and you get a Jupyter Hub node in the cloud in the same region as the data. So you get that nice fast access to the data. And that's also deployed with DAS Gateway for scalable compute. So if you have a big job, you can quickly spin up DAS clusters to distribute the work on a whole bunch of machines. And then all of this is in service of environmental sustainability. And so that's why we're working with others to generate these applications, which kind of take the data, uses the APIs and all the insights from the hub, puts them together into applications that decision makers can actually use to make informed decisions. Okay, so quick introduction to STAC, since I'm guessing most people in this group are somewhat familiar with it, but spatial temporal asset catalog. There's two main parts to it. So the first is a specification for how these JSON documents that are capturing the metadata of these geospatial data sets, what those JSON documents should look like. So what keys they should have, what the values should represent, things like that. So there's like a core STAC standard that says things like, a STAC item has to have these fields like an ID, a geometry, a date time, things like that. And then there's a whole bunch of extensions for adding additional metadata. And so we'll see those in action in just a bit. But that's kind of the core part is a stack specification for how you should capture metadata about these spatial temporal data sets. And then the second part of STAC is an API for saying how clients and servers should communicate with each other to actually make this data accessible. The most important part of that is the search endpoint, where you can make spatial temporal queries to find specific subsets of the data that you're interested in. And we'll see that in action, but just kind of have it as a little preview is, imagine that you've gone through all the work. Or we have gone through all the work of getting files into Azure Blob Storage in analysis ready format. So these are cloud optimized GeoTIFFs for Landsat 8, collection 2, level 2. And now you want to answer a kind of, basic question is like, give me all the cogs covering Wyoming in 2016. And if all you had was a collection of files on blob storage, it's kind of hard to do that. Like you're stuck, like there's dates in here somewhere. I'm not quite sure. There's like multiple dates. So I don't know exactly which one refers to the time the images were captured. There's probably some way you can figure out like where on Earth each of these cogs is covering, but it's not exactly straightforward. So you might have to be opening up individual files. And then if you want to like take this knowledge, answer the same question, but using like NAPE or Sentinel-2, that's going to have a completely different naming scheme. You're going to be, having to reinvent all of that. So that's why that's like the very first way that STAC is very helpful is it gives us this standard to describe these spatial temporal assets, in this case, these cloud optimized GeoTIFFs, a standardized way to capture the metadata, like where on Earth is it? What's the date time? Things like that. And with all that structure, we can build APIs like the search API on top of that. So quick little example here, but we'll actually jump over to a notebook to actually run through these. So now I'm on the Planetary Computer Hub. I've already logged in and started up my server, but this is just a basic vanilla Dask hub deployment. So you get a Jupyter Hub, which you can use to start up single user notebook servers like I have here. This is running in West Europe, so the same region as the data. And then you also have the ability to create Dask clusters, but we won't be doing that here. We'll be using Dask, but just on a single machine. Okay. And the idea behind this notebook is to go through each of the different kind of data types that we're offering on the Planetary Computer and see how STAC is useful for each of those. Okay, so the first one is kind of a similar sort of thing to a question that we were trying to answer earlier, is like, give me all of the, in this case, Sentinel-2 scenes covering some area of interest. So here's our area of interest expressed as a GeoJSON polygon. And we want all the items covering this month or two here. And we can also do nice things like query for just the items where the, well, unarbitrary properties, but in this case where the cloud cover is less than 10%. So when ESA is generating these cogs, they have some way of determining how cloudy each image is. And that's included in the metadata. Okay, so then we quickly do the search. In this case, we're using PyStack client, but STAC is like language agnostic. It's in this case just REST API calls, but PyStack client makes it nice and easy to use. And we, in less than a couple hundred milliseconds, we found the 5 items that match our query. So each of these items is a Sentinel-2 scene that has a whole bunch of metadata associated with it. And then the most important thing are the assets here, which link to the actual cloud optimized GeoTIFFs themselves. Okay, let's scroll back up. Sorry about that. These STAC items are actually GeoJSON like features, I think is the right term. So we can actually stick them in a GeoPandas data frame and check out and see. So here's our area of interest in yellow. We put in that layer for this leaflet map, and then we also have our the items that intersect with it. Okay, in this case, we're looking at this area in Alaska. Okay, we'll grab the least cloudy item here. It's actually the big one here that covers our AOI entirely. And then one quick thing that's not really part of the STAC standard, but that the Planetary Computer uses for kind of access control is this signing idea. So if I just try to open up this asset here, I'll print out the link for you. This is a link to the cog in blob storage, but this is in a private blob storage container. So you can't actually just download this URL. You need to sign the items. And that appends this read-only short-lived SAS token, so like shared access signature, I think it is. So it appends this token to the URL. And that's mainly for us, for the Planetary Computer team, to kind of keep an eye on what data is being used, and most importantly, making sure that a ton of data isn't leaving West Europe, basically, just to keep our egress costs down. So when all the Planetary Computer metadata STAC API is you can use completely anonymously, no account. You can also sign assets anonymously. So you don't need a Planetary Computer account to use the data or the STAC API. We do just prefer that when you are using our data, wherever possible, keep the data in West Europe. That keeps our costs down, especially on the egress cost side. And it's also like the best for the user experience because it's the fastest bandwidth going from blob storage in West Europe to compute in West Europe. Okay. And then, yeah, I should say while I'm mentioning this, don't need a Planetary Computer account to use the data or the STAC API. You do need an account to use the Jupyter Hub, which I'm logged into right now. Okay. So yeah, so we've got this STAC item. Matt showed off using ODC STAC, which is this new tool for going from STAC, a STAC item or collection of STAC items to an X-array data array. Similar sort of idea with STAC. It's the basic idea is going from metadata only contained in this JSON document, these lists of JSON items, to a data array. We have all the information we need from things like the geospatial projection here is EPSG 32606. We know exactly where on Earth it is in the XY coordinate space, thanks to the geospatial transform. We know the resolution. We have everything we need to be able to go from STAC item to X-array data array, just using the metadata. And then when we go to actually compute on that, DASC and X-array and this whole tool chain will know that, oh, to read this pixel here, I need to read this window from this cog. So all that metadata is there. So if we want to do a quick little computation, we'll compute in DVI. So select the red and the near infrared bands here and compute that. Yeah, there's a question from Ted. This X-ray is just metadata. Yeah, so at this point, even up until here, where we're computing in NDVI, but definitely here after STAC, it is just metadata. We haven't opened any cogs yet. We haven't read any actual data in. It's not until we call persist here that we actually compute something, and that's when the DASC task started executing. Now that we have the NDVI in memory, we can plot it here. This is using stack.show. Quick little way to get this interactive map, and you can pan and zoom around. And as you, I think, zoom in, it'll like do the higher resolution calculation on just this window here. Yeah. Okay. So that general idea is useful for if you're dealing with a single item, which maybe you could do on your own just by like opening up the file. It wouldn't be, or the files in that case, one for each asset. It wouldn't be too slow. But if you have something where like a much bigger area of interest, a larger date range, in this case 255 items, it'd be really too slow to open up the 4 assets per item in this case. But STAC or ODC STAC is able to do that very quickly, since it's just operating on that metadata. So we now get this large data array there. And I should have said, if you have any questions, feel free to interrupt as we go. And Sudhir had a question, is there any way to query the location using the map view and selecting that extent as well? I don't know, I think you can. So this is just an IPy leaflet map. Can you get like the window? What's this, window URL? Nope. I think there's some way to get like the bounds of the window, but I don't know how to do that offhand.
Okay, thanks.
Because I think, yeah. Go ahead. Okay, I think STAC's actually using that in the background to figure out which assets to read in, which windows to read. Okay, let's see. Cool. Next up is Earth systems science data. So this is going to be typically higher dimensional data, like weather or climate model outputs. That are often stored in NetCVF or on the cloud, typically stored as ZAR. In this case, we're going to be working on TerraClimate data set. And I want to show one important thing about STAC before we even access the data here. It's really flexible. So the core STAC specification just needs like ID, this type, links, maybe some assets, but really not much. Most of the other stuff here, in particular, things like the cube : variables, which we'll see in a sec, and the cube : dimensions, these are coming from STAC extensions. So adding additional metadata to the STAC documents. So in this case, we've actually taken the ZAR data set and parsed some of the metadata out of it. So looking at what variables are there, finding those, and then for each of those variables, getting things like the units, various adders, shape, chunks, and the dimensions. And we're able to take this JSON document and transform it into this nice HTML view here. If you're just browsing, what data sets are available on the Planetary Computer, you can quickly get an overview and go into what exact variables are available. So like snow water equivalent has dimensions, time, latitude, and longitude. These chunks, the shape, these attributes. If you're doing stuff with like CF conventions, that's all there in the metadata. Okay, so back to the data access side, we're going to read in this collection, and this collection has various assets. So in this case, we have one asset for, well, a thumbnail, and then an asset for accessing it from using the Azure Blob file system protocol, which uses the library ADLFS, and then a second asset for if you're accessing it through HTTPS. So we use the HTTPS asset. That has some additional fields here that we've included, which is using another STAC extension called X-ray assets. And this is a way to encode additional metadata that would be useful if you're using this tool chain of ZAR, FSPEC, X-ray. So this is helpful to go from STAC collection to an X-ray data set in this case. And the only two kind of pieces of information that we needed in our head were the key of the collection and then the key for the asset that we were using. Anything else like, what additional fields do I need is all there in the STAC metadata. That's nice because you don't have to remember this stuff around like, what's the storage account name, what's this long URL, the path within the ZAR, within the container, things like that. All you need to know is the key for the collection and the asset. At that point, do stuff with it. So in this case, we'll slice out a region over Washington State and look at vapor, water vapor partial pressure. I don't know if that's meaningful or not. Or you can do time series type stuff, pretty common with ZAR. So this is chunked, it's monthly data chunked yearly. So it's kind of nice to have that chunking along both dimensions there. I have no idea what happened in 2000 or 2001, whenever this was, but the vapor pressure, partial pressure dropped precipitously for some reason. Cool. Any questions on ZAR before we move on?
Is the extra args, is that something that might end up in some like modeling extension to STAC or something?
What do you mean by modeling
Well,
extension?
Yeah, I don't know really.
It did just end up in intake stack. I don't have the main version from GitHub installed, but intake stack, well, intake, I guess. If I spelled it right, it has like an intake.open stack collection. So you'd pass it the URL to the stack collection, and then you would select the ZAR HTTPS and then call .to dask. And so as of last week, the GitHub version of intake stack will automatically know to look for X-ray open quarks and things like that.
Okay.
Maybe that answers your question.
And that to dask is creating a dask array.
It's creating in this case an X-ray data set, dask back X-ray data set. So intake looks at the type of the data, like the media type. It sees that it's a ZAR data set, and intake ZAR knows to use X-ray data sets for ZAR data sets. And the to-dask says use a dask-backed version. Amy, did you have something?
Yeah, I had 2 questions. So what is this X-ray open quarks?
Yeah, so that's another STAC extension. I don't think it's in the official list, but STAC extension / X-ray assets. It's additional metadata for saying, how do the basic motivation is something like writing a library like intake stack to go from stack item to collection, like data container, without having to rely on additional information from that would typically be in the user's head. So in this case, it's helpful for something like this
X-ray or for ZAR.
Yep. So it's specifically for, well, it's for X-ray. I haven't tried it on NetCDF, but other people are. And yeah, it's just helping out with this tool chain of stack to X-ray.
I think that's what I guess that's what I really meant was, yeah, I mean, X-ray is sort of the modeling extension, if you will. Then.
Okay.
Like, I mean, right?
Yeah.
Like it's an X-ray extension, not a modeling extension, because X-ray can handle. Yeah. Okay.
Okay. Yeah, my other question's kind of related, which is just, is there sort of a way to get from a stack query to a specific ZAR query? So like previously you were querying your cloud optimized geotiffs for a spatial extent and then opening that data set with that spatial extent, but I don't see that there's currently a way. This isn't really a planetary computer question.
Yeah. No, that's fine. This is something that I'm really curious into, because like we kind of have 2 different. It's kind of from one point of view, it's 2 different like APIs for I want like this subset of data, and if you're using like cloud optimized geotiffs, you're going like stack to X, like something like stack, which will do some of this clipping for you. Searching for this AOI and then getting out that subset. If you're using ZAR, you're kind of going stack to X-ray and then doing the slicing, which is different. And like you kind of have to know that. So like that's the state of things right now. I'm curious about what people think about, like, what do we actually want? Are people okay with that difference, or yeah?
I don't know. I mean, because it seems like in the first case, we've built tools to make it more seamless. But in this case, you could do that, or you could leave it like not, sort of black magic or behind the scenes and leave it like explicitly part of the X-ray API.
Yeah, it's like X-ray knows how to do slicing. So, that's it's like able to do that already. And so that's kind of why I'm leaning on that. I don't want to necessarily reinvent that. That would have some implications on the stack data model side of things. So right now there's a stack collection, or in this case, we're using a collection or a single stack item for the entire ZAR data set. So it's just
Right.
passing the path to the root of the ZAR data set. You could imagine something like a stack item per chunk of a ZAR data set.
Yeah.
So then you could read in the chunks, like maybe that makes sense. I'm not quite sure.
Okay. All right. Yeah, I mean, the problem makes sense, or the solution, I guess, makes sense to me now. So,
Yeah.
okay, go ahead.
It's definitely an open question though. And maybe like, so we'll go on to a completely different example
Hey,
now.
Tom?
Yeah, go ahead.
Could you scroll back up to that display of the metadata in the table for a second?
This one or?
Yeah, because some of those variables have a metadata element called standard name. Would be nice if you could throw that in here, because that's that's the interoperable name for those data sets. So Q being runoff amount may not be obvious to everybody.
Yeah. That's a good point.
Standard name is really the shared name for that concept.
Yeah, so this would be like
That's
what
the
is this?
variable
Variable name. Yeah, okay. And then standard name would be good to lift out there. Okay, cool. And standard name, is that a CF convention thing?
Yes.
Okay.
Right. Okay. Now we wanted to change variable name to cryptic name, but no one would agree to that.
That's pretty good. Okay, cool. Yeah, I'll pass that along. We should be able to lift that out as we're generating this metadata. Yeah. Cool. Okay, cool. Oh, and I should share this. Guess you could have on perhaps. Here we go. I'll share the URL to the notebook here in the chat. Hopefully that loads.
And actually, this isn't a planetary computer question exactly either, but I think, Tom, you might know about this as well. Like, slicing only works if you have one-dimensional longitude and latitude coordinates, right? Like, but there's work on adding multiple axis or multiple dimension coordinate axes support to X-ray or something.
Yeah. So this data set happens to be in what is that, WGS 84. So I could slice with latitude, and that's its native coordinate system. But if you have some projected coordinate system, you need to be doing this slicing in that coordinate system or relying on these tools. I think it's like XOAK. XOAK is maybe a prototype, I'm not sure what stage it's at, but a way to have these like I forget what it's called, like indirect or alternative indexing schemes.
Yeah,
you could index using latitude, longitude on a projected data set efficiently.
Rich, I'll try and put some links in the chat here, just for the new X-ray Roses grant that they just received to undertake some of this work. And then there's a good issue on the STAC repository detailing some of this. And then also Gabe Joseph is actually giving a presentation later this week around some of the like longer term vision for STAC stuff at the ARD workshop.
Oh, nice.
Be helpful on that as well. I'll put links for everything.
Thank you.
Yeah, so the last data sets, Parquet data, U.S. Census is I don't know if my internet's slow or what. Hopefully the audio is coming through fine. Oh no, that's not good. I think my Zoom seems to be fine. So Zoom is right now. Yeah, okay. We will let it. How's it now? Still
better, but it's a little
better. Okay, sorry about that. Let's plow forward. And hey, Rob Emanuele is also on the team, showing STAC questions for him. Direct them that way. In this case, US Census, we're modeling as a whole bunch of Parquet data sets. So a bunch of stack items. So one stack item per Parquet data set. And the way the US Census is structured, they have these. So here's all the stack items, one for each Parquet data set. So the census is built up from the block level. So the census block level is the smallest unit. They get like population and things like that at the block level, and then aggregate them at things like the state and the region, voting, various voting districts, things like that. So we can do things like grab the geometries here. Okay. So these are the geometries of each census block. There's like hundreds of thousands of them, maybe more. We can read in the population table by grabbing that population key there, that stack item. And then if you use STAC data frame, you can do things like efficient random access based on partitions. So 44 is the FIPS code for Rhode Island. So if you grab the first division with the 44 FIPS code and slice on up to whatever the highest, we can very efficiently. So we only read in 2 Parquet data sets here to get all of the census blocks for Rhode Island, the 20,000 or so for Rhode Island. And then we can do things on that, like plotting the joint distribution of population against land. So population, high population, small census block. So this is like high population density, low population density over here in this corner. Do things like plotting all of the ones with more than 100 in the population. So some census blocks are actual blocks. Other ones are a bit larger, especially if you get into less populated areas. So anyway, using STAC again to kind of kick off that analysis. So we're finding, using a collection for all of the stuff in the same group of US Census, and then one STAC item per Parquet data set. Each one of those is a link to the root of a Parquet data set that can be read in. Again, we're relying on like FSpec and Azure ADLFS. Okay, cool. Quick little wrap up here. We saw these different types of remote sensing data. Each of them start with STAC, which has been great to have a consistent metadata catalog for each of these various types of data. And then using various tools to get them into a hopefully familiar data structure, so like an X-ray data array or a pandas or geopandas data frame. And then from there, doing your analysis. That is, I think, it for me. So yeah, hopefully we have some time for questions, discussion.
Yeah, thanks, Tom. I guess I'll kick it off. How automated is the production of these STAC metadata for different data set types, ZAR versus COGS versus tabular?
Yeah, I'll put a couple links in the chat. So for ZAR, there's this little utility called XStack that I think Sean has used, so he can comment on how well it actually works. But the idea is you pass it a path to some ZAR group. So in this case, Azure Blob Storage or whatever, anything that can be opened with FSpec. And it'll take the ZAR metadata and build up these STAC items, STAC collection or items. So that works pretty well. And then for tabular data, similar idea, you pass it a path to a Parquet data set. I think it's the only thing that works for STAC table, and it generates these like the columns. I don't think I showed any of the items for items. Nope, that's not gonna work. Any of the items here, but this has things like the limit equal to 1. It has like the columns. I think it's table : columns for each of these tables. So I think for Parquet and ZAR data sets, it's pretty good because they tend to be pretty structured. Generating like the STAC metadata for some very complicated data set like Sentinel or GOES, I think is pretty challenging still.
Okay, I could imagine you could do something simple but not get all the data that you probably need in there.
Yeah. Do you mean for the remote sensing data sets or?
Yeah, like cloud optimized geotiffs, like you could
Yeah.
at least get like, often you could probably get spatial and temporal
Yep.
data and band data.
Yeah, especially if you have like a convention of how like dates are laid out and spatial stuff. Yeah, that's definitely more feasible than something like GOES has been really challenging. Just ask Rob.
Yeah. NetCDF HDF would probably be an entirely different story.
Perhaps, yeah.
Well, it's pretty easy to extract metadata from NetCDF or HDF, depending on what the structure of the data set is.
Right, if you know the structure of the data set.
You actually don't need to know that, right? Because the metadata is the self-describing part of the NetCDF. So, but my question is, Tom, the other day we talked about that the STAC database that you're using to do these searches. Is that database described somewhere?
Describe like the
Schema or something?
Yeah, I'm not actually sure. I'm guessing you could get it from, and Rob will actually probably correct me, but we're using PG STAC, so I think it has like a fixed schema for how these get ingested.
Yeah, I guess, are you talking about the schema of the database itself or just like the data that it's holding? Because it really just holds STAC metadata. So the schema of the metadata information that's contained in the database is STAC items and collections.
So it's a JSON database?
It uses JSON-B columns in PostgreSQL to, yeah, hold the JSON data directly.
Yeah, okay.
Mostly, there's some columns that are exploited out for you know, the datetime and like collection ID and things like that. But yeah, the entire, if you click on that SQL folder, then you'll see like the entire setup pretty nicely separated out into different SQL files of how the database is set up.
Thanks, Rob.
Thanks. Looks like Julian has a question.
Hi, yeah, this is Julian from Unidata. I'm curious, what happens to your notebook after you log off or whatever? Will that notebook that you just built up persist?
Yeah, so this is in my home directory here. If I navigate all the way up, which, yeah, there we go. It's in this home directory here. So this persists across sessions, everything in here. Anything outside of this home directory is reset each time I stop and restart the notebook server.
And it just persists indefinitely as long as you have a Microsoft account, I guess?
Yep, Planetary Computer account, yeah.
Okay, and then second question is, how much does this cost?
So there's a few things, a few different services running here. So we saw first of all, there's the data, hosting that data in blob storage, which costs something, and my internet's dropping out, post in chat, sorry. So there's the data blob storage, which costs something, and then there's like egress charges on top of that when data is leaving the Azure region. There's the database. Well, I guess, yeah, so then there's the web server, which is deployed in Kubernetes, but it's not doing a whole lot. It's responding to queries from clients and then passing those off to the database. So then the database is doing a good chunk of work. So you can scale that up or down depending on the volume of requests and complexity of the queries and things like that you're looking to support. And of course, like the number of STAC items that you have. But that database is a depending on the scale is going to cost more or less. We happen to be using Azure Postgres flexible server for ours. And then it's like that's the kind of like back end side you could think about it. And then there's the hub. We're running ours in Azure Kubernetes service. So there's the cost of a little node, like a tiny node to sit there and wait for people to like log in and things like that. So there's the Jupyter Hub stuff. When somebody logs in, it starts a node for them. So there's the cost there is then, as long as this person is logged in and using their notebook here, there's a cost associated with running that node, whatever the cost of that VM is. There's a bit of cost for this user home directory. And then the last thing is the task workers.
Yeah, and just to clarify, the cost to the users of the Planetary Computer is 0. That's all the costs like incurred by Microsoft for hosting it.
I realize I might have
Yeah, and Tom, you're breaking up again, unfortunately.
So I guess related to that, this is also so every person who's signing on to the Planetary Computer notebooks has a login, and so that's also being used with the sign. Is that the same thing that's being used with the Planetary Computer Sign API?
Yep.
That's right.
Oh, it seems like you're back, Tom. So go ahead.
Mike, I think.
Yep. No.
Yeah, I don't know if I heard my name, but this is Micah from NOAA. Great presentation. Thanks, Tom. First, I put in a request for an account, so I don't know if you guys have the authority to approve those, but that would be awesome. My question, I guess, was more to do with the data catalog on Planetary Computer. And I noticed, like, if you're looking for a collection, basically through the search interface, you're limited to the keywords that are listed in the STAC collection metadata. And I'm just wondering if there were any ways within STAC to enhance that. Like, say, for example, Ted's example of listing the standard name in a data set. Is there any way to sort of extend those capabilities beyond just sort of arbitrary keywords in the STAC collection metadata? Or any plans to enhance that?
Yeah, so I think there's an open issue in the STAC API repository about collection level search. So right now, if you go to API/STAC/v1/search, this is all about searching on item level information. So there's that avenue of, if you want to do things like through the STAC API, like how do I figure out some facet of a collection that's not implemented through STAC yet. This little keywords thing is just building off of some metadata that is part of the STAC standard, which is keywords. So then the other thing we could do is somehow enhance this little whatever logic here to also look at additional fields, perhaps, or stuff more into the keywords. That's something that we could do without necessarily API to evolve something like a collection level search. And the last thing we can do is our systems data sets are stored as collections rather than items. So we're make them available as items as well. So like TerraClimate as well. You would be able to search on things like, give me the thing with name equal to whatever that variable. We think we should be able to do, but we haven't.
Yeah, hopefully that came through. But just generally recap, like there's collection level search, a standard implementation in STAC API that's coming probably in the next 6 months, I'd say, and then we would implement that type of search on our collections, because that's becoming a problem of just like too many collections, and we need to like better be able to filter those down and accept just through tags.
Cool, thanks.
A search based on standard name would be a great example of sort of the benefits of standardization. You guys are doing such a great job of trying to standardize across a wide variety of data sets, and standard name is something that some of us have been using or trying to encourage use of for years. So welcome to that help. Thank you for being helpful for that group.
All right, well, I think we're just about at time, so I think unless there's anything super burning, we can leave it there and appreciate so much, Tom, again, you joining and giving this presentation, and also Rob for supporting today. Yeah, just thanks so much, everyone, and I'll see you all next time.
All right, thank you.
Thanks.
Thank you.
Thanks,
Amy,
everyone. Have a good
Amy.
day.